In this video, we'll show you how CNNs see. Not just to explain the math, but to give you an intuitive sense of why they are so good at analyzing images and videos. We'll do this in 3 parts. First, we'll start with why even needed CNNs and how they have evolved to give us all the popular names that you hear, like AlexNet, ResNet, etc. Second, we'll go under the hood to see exactly how a CNN layer uses digital stencils to scan an image. Third, we'll see the big picture of how the AI combines all these tiny details to make a final intelligent decision. Welcome to Scovia, where we make AI concepts feel like everyday ideas. Let's start with why do we even need CNNs? Why did the researchers come up with this neural network architecture? CNNs weren't an overnight success. The concept was famously introduced in the 1998 paper Gradient-Based Learning Applied to Document Recognition by Jan LeCun and his co-authors. They started by teaching computers to read handwritten zip codes. From those humble beginnings, the architecture evolved into legendary versions you might hear about in AI circles like AlexNet, VGG, and ResNet. Researchers loved giving these networks fancy names, and theoretically, anyone can design a network. But the issue is that only a few of them, like the ones you see here, will actually work well on real datasets. Before CNNs, we used standard neural architectures. They worked great for spreadsheets, but for images, that's where things got messy. Think of a standard digital photo. It's a sandwich of 3 color layers: red, green, and blue, RGB. Each layer is a group of pixels. If you take a standard 224 times 224 pixel image, and if you flatten it into a long list of numbers to feed a regular neural network, you're going to hit 2 massive walls. One is the math explosion. That one tiny photo has about 150,000 numbers. If your first layer has just 1,000 neurons, you're looking at 150 million connections to track. It's like trying to memorize a whole library just to recognize a cat. The second problem is that flattening an image is like putting a photograph through a paper shredder and then trying to tell what the picture was. Flattening scrambles that neighborhood information, and the AI has to work incredibly hard to relearn which pixels are neighbors. Whereas CNNs understand proximity right out of the box. This brings us to our second part of the video. How does a CNN layer work? CNNs solve this by using 2 clever assumptions. Local patterns matter, so you look at a neighborhood of pixels instead of 1 pixel at a time. The second is translation invariance. If a layer learns to identify a specific shape, it'll find that shape no matter where in the image it pops up. This makes the model much more robust and lighter to train. A CNN is essentially a stack of specialized blocks. There's the convolution layer, the activation, which is typically a ReLU, pooling, and then you repeat this block many times to form the architecture. The final layers are usually the dense layers, followed by a softmax if you're doing a classification. So among all these layers, let's look at the star of the show, which is the convolutional layer. A convolution layer is essentially a layer of filters. Unlike a typical neuron, which accepts a number, each of these filters work on a block of pixels in the image. You can think about a filter like holding a small stencil and sliding it across the image like a magnifying glass. Each filter looks at a tiny 3 times 3 square and it multiplies the pixels by its own weights and then it sums them up. That result becomes a single dot or a single pixel in the new feature map. In a real color photo, a filter isn't a flat square. It's a 3D cube, which takes into account the red, green, and blue layers in the image. And the CNN layer doesn't just use one filter. It uses hundreds of them in a single layer. One filter may highlight vertical edges, another might find curves, another might spot some honeycomb textures, etc. As the image moves deeper into the network, the AI builds a hierarchy. It goes from seeing pixels to edges to shapes and then finally to objects. You might be wondering, what are these numbers associated with each filter? These numbers are the model weights. We don't know ahead of time what they need to be. The idea is that you start with a random initialization, which are obviously completely wrong, and then during the training process, the model automatically learns what these numbers are supposed to be in order to make the right prediction. Typically, for each new type of architecture of CNN, the authors will publish how many parameters the model has, which is the total number of model weights. If your model has a large number of these filters, it'll obviously have a large number of model weights. It turns out that when designing a network architecture, there are more things you can control about it. One of them is stride, which tells us how far the filter jumps. A stride of 1 is a slow, careful crawl where you don't skip. A stride of 2 is like a brisk jog, where you skip a pixel when you're sliding the filter across the image, which means that the outcome is going to be much smaller, like 1/4 the size of the original image, right? The second one is padding. So we add a border of zeros around the image so that the filter can reach the very edges without falling off the map. After convolution, we apply an activation, which is usually a ReLU. Without activation, your whole network becomes basically one giant linear function. ReLU makes the network capable of learning complex patterns fast, so it adds that nonlinear element to it. This brings us to the third part of the video. How do we use CNN in the big picture to make a prediction? Turns out, this involves a few other layers, which are simpler than the CNN. One of them is pooling, which is the compression step. The classic one is max pooling, though there are other types as well. So what you do is you take a 2 times 2 region, and then you just keep the maximum value. And you do this across the entire image. And what this does is it reduces computation and it adds robustness, which means that small shifts in the image don't break your prediction. Also note that modern CNNs sometimes replace pooling with strided convolution. The goal is the same, which is to reduce the spatial size while keeping all the useful information intact. So after several convolution blocks, you have high-level feature maps. And once you're happy, you'll flatten them, which means you create a list of numbers. So it's like a flat list of numbers. And then you feed them to a dense layer. And then use the Softmax in the final layer so that it can now output probabilities. Like, for example, if you're trying to predict one of 3 categories, cat, dog, and car, then it'll output something like, oh, I think there's 98% chance that there's a cat in the image, 1% chance that there's a dog, and 1% chance that there's a car. So that's the basic CNN. Now let's answer the bigger question. Why did this beat the older approaches so hard? Before CNNs dominated vision, many systems worked in the following way. Humans designed features, edges, corners, textures, etc. And then they would train a classifier like an SVM. This worked, but it had a ceiling because humans were guessing what features mattered. CNNs changed that by learning features automatically from data. Early layers simply learned low level features like simple patterns like edges, and deeper layers learned more complex concepts like faces, wheels, text, and things like that. So instead of hand engineering vision, CNNs learned the features as well. So they learned it end to end. CNNs became dominant because they combined three great qualities. One is that local connectivity, so they are able to focus on a bunch of pixels at a time. They shared weights, which means one filter could convolve across the entire image, so it worked everywhere. And the third is, and using layers of these, it was possible to build hierarchical features. This made training possible at scale. And once GPUs and the big data sets showed up, CNNs just exploded. Wait, these networks have millions of parameters. Normally, that would take years of training and ton of data to train. However, most people are able to accomplish good performance on most tasks, even with a few images, and in just a few minutes. So, what's the secret here? And if you wanted to build one today, which architecture should you be picking? We'll answer those questions in our next video that focuses on architectures and transfer learning, where we'll also share some sample code. Thanks for joining us on Scovia Labs. Hit that subscribe button for more eye-opening insights, and as always, stay curious.